What's up, scholars? Today we're talking about the quadratic formula. Now, why are we talking about the quadratic formula? Well, because quadratic modeled things in the world happen pretty frequently because of gravity. What do you mean, gravity? Well, say, for example, we had some sort of object and it got tossed up in the air and then started falling down. Things that fall on our planet will always behave in a quadratic fashion and adhere to some equation, like the height of that object at any time t is equal to some term a times the time that thing has been in the air, plus some term b times the time, plus some constant term, which is its initial height, the height where it started. So this at squared term is going to dominate this function, and that means the function is going to behave mostly like the parent function t squared. As you zoom in either direction, these terms kind of fall off. They don't mean as much. It behaves more and more just like this t squared function. But since this dominates, the reason it dominates, I guess, is because of this a term, which is the acceleration due to gravity. Okay, gravity is the biggest force happening on objects in what's called projectile motion. That's a longer discussion to have with your physics teacher, but anyway, quadratics are really popular on Earth because of gravity. So, quadratic formula, why is that useful? Well, these quadratic functions that model lots of things that are related to how things fall in gravity really only have 3 points that we usually ever care about, to be totally honest. We're interested in the most extreme point on the quadratic equation, i.e. the maximum or the minimum. That's usually a point of interest. Like if it's some projectile, we say, well, how tall does it ever get? Where's the vertex? It's up there. We are also, so let's just go ahead and say we are interested in the vertex, and then we're also interested in where the function equals 0, aka crosses the x-axis, aka has some roots. Remember we call these guys the roots, the intercepts, the solutions. What's the other one? Roots, intercepts, solutions, zeros. Also called zeros. I never know if there's an E there or not. I don't know. Why are these points interesting? Well, in a real world function, if this bottom part here was our time and this vertical axis was our height, then we wouldn't really care about the before time because that's not real. But we would say, when is the object going to hit the ground? How tall does it get and when is it going to hit the ground? That's all I really care about. How tall is it going to get and when is it going to hit the ground? The quadratic formula tells us these things. It tells us these really important, interesting points. And interestingly, these things are always related to this thing. So if you know the vertex of your parabola, and you know whether it's a really skinny parabola or a super wide parabola, so you know the coefficient in front of the first term, telling you how fast it's growing, then you'll always know where these are. And the reason is because these solutions are symmetric across that vertex. So if you know this, and you know whether it is a narrow parabola, a kind of normal parabola, or a wide parabola, if you know that, you will always know the roots, intercepts, solutions, or zeros. So if you know the vertex, you will know the solutions. And that, my friends, is where the quadratic formula came from. It came from saying, okay, if I know where this thing is, then I know where these things are. It uses a bit of mathematical gymnastics called completing the square, which admittedly is not my most favorite of the tools in the toolbox, but you know, it's useful for coming up for things like this, when I want to know things like this, based on just that. It's not really just the vertex, it's the vertex and the initial height. The initial height. Where are we starting? Initial height. So if I know the vertex, how tall it gets, and where we started from, which those are reasonable things to know together. If you know where you start from, you know how tall something gets, then you could know when it's going to hit the ground. These are both height related situations, you know. So let's think back way to Algebra 1 days. There was an equation for a vertex. The vertex was negative b over 2a when we talk about a quadratic in standard form. And the initial height is some value c. So we got our a and our b and our c. Cool. We're going to use all that stuff to derive the quadratic formula. It is going to get a little bit weird. I would recommend pausing this video multiple times as you need. Okay. So we're going to take our standard form of a quadratic, being y equals ax squared plus bx plus c. What did we say? So again, yeah, our a and our b coming from our vertex, our c coming from our initial height. Right, vertex and initial height. So what are we trying to use this thing for? What we're trying to use this thing for is to figure out where these points are. Where do these points happen? These points happen where y equals 0. So we should set this equal to 0. 0 equals x squared plus bx plus c. Because at these points, the y value equals 0. Okay, cool. So think about it again. What are we trying to get to? We're trying to get to an answer for x. So at the end, our goal is to have something that says x equals, because I want to know where on the x-axis these y values are 0, where these things happen. Where is x? All right. So we're going from here, trying to get to there. X equals something. Gotcha. Do you remember way back when you'd have something that was like x plus 1 squared equals 9? And you're like, gotta solve this for x. These are so easy. I love these ones because I just square root both sides. And I get x plus 1 equals 3. And then voila, x equals 2. That was so fast. We're going to make this situation happen. The x plus something squared is going to equal to something. So that we can use this technique and square root both sides and then subtract some number from both sides to get x equals something, which will get us to our goal of x equals something. Because what are we looking for? We're looking for these roots. We're looking for these places where x equals a value such that the y value of those spots is 0. Is 0. So trying to get this situation out of this situation. What does this situation look like? Well, it looks like x is by itself. It looks like there's nothing in front of x. Alright? Let's get, I know I'm going to have a squared here. I got a squared here. Let's get this something out of the way. Because this something didn't have a thing. Right? There was no number in front of this x. Let's get rid of this number in front of this x. How do we do that? We divide everybody by a. Everybody gets divided by a. 0 divided by a is 0. Ax squared divided by a is just x squared. We're getting somewhere. This is now plus bx over a, and this is plus c over a. Okay. Okay. So, here's where the completing the square part is going to happen. Okay, so hear me out. Hear me out. Let's say, for example, we had x plus 3 squared. If we expanded this out, what would we get? Well, this would be x plus 3 times x plus 3, right? Yeah. Okay, well, what is this? Well, this is x squared plus 6x plus 9. Now, how are these numbers related to that original number? So this number is half of that number, and this number is half of that number squared. That will always be the case. This one is half, this one is half of this number squared. Okay, cool. So we're going to try to reverse engineer this situation. We're going to go from this guy to this guy to this guy, so that we can get some squared thing equals something, so that we can square root both sides, and we'll get an answer. Ooh, I forgot to do a plus and minus here, didn't I? Oh, dang, dang! So our answer is 2 and negative 4. That's a real important deal there, that plus or minus. When you square root both sides of an equation, sometimes the minus won't make any sense, but mathematically it's correct. So anyway, we're trying to go from this situation to this situation where this term is half that term and this term is half that term squared. Let me write that down. 1/2 of the b term and that whole thing squared. Half the b term squared. So we want to make this look like that. So we make it like this, make it look like that. So we do this. Woo! You ready? About to start getting real crazy up in here. Okay, so we have an x squared term. Cool. We've got some term in front of an x. We need to make this last term only related to this term, 1/2 of this middle term squared. So we're going to move the third term over to the other side, get it out of the way. Minus d over a, minus d over a. And then I'm going to rewrite this equation on the back of this sheet of paper so we can keep going. So here's where we are. Negative c over a, because we subtracted c over a from both sides, equals x squared plus b over ax. Again, we're trying to go from, this is our muse, from here to here. So we're going to add a term on both sides, which is totally legal. You can always do that. You can always add the same thing on both sides. That doesn't change the equality as long as it goes on both sides. So we can add whatever we want. So we can add half of this b term squared. B being whatever is in front of the x. B being b over a, which is in front of the x. So we're going to add x squared b over a x plus b over 2a, because that's like b over a times 1/2 squared. So I'm adding this term. But if I add it to one side, I have to add it to the other side to maintain equality. B over 2a squared, where that 1/2 comes in. Why did I do this? Because I was trying to get from something with 3 terms to something with 2 terms squared. So, this shortcut here, going from this to this, how does this relate to that? Well, this becomes x plus b over 2a squared. Right? What do you mean b over 2a? That's 9. Well, this 9 was half of the b term, which was this 6, which in our case was a b over a, so it's half of that, so it's b over 2a. Alright, so that equals this mess over here. Negative c over a plus b over 2a squared. You pausing yet? You probably should have paused. This is a tough one. This is an algebraic proof at its finest. What was the point of this? Because if we had something that said something along the lines of x plus 1 squared equaled 9. Got ahead of myself. Then we could square root both sides, and we'd say x plus 1 equals plus or minus 3, and we could subtract 1 on both sides. We can get those x's real quick, like 2 and negative 4. We're trying to get x by itself because we're trying to get this quadratic formula that solves the equation for the zeros, the roots. So now we're at this step. We're going to square root both sides. Square root both sides. Square root both sides. Well, this isn't bad because when I square root a squared, I just get x plus b over 2a. This feels slightly strange. This negative c over a plus b over 2a squared feels a little strange. You know what? Let's just blindly go with what we got. So this is negative c over a. If this is squared, okay, I could say that's b squared over 4a squared. Fine. Equals x plus b over a, 2a. If I wanted to add these two fractions, these denominators would need to be the same, so I should multiply this by 4a on the top and the bottom. So this will be negative 4ac over 4a squared plus b squared over 4a squared. Why did I do that? So I get add those two together. So I get negative 4ac plus b squared all over 4a squared. I'm just dealing with the left side of this equation right now. This is starting to kind of look familiar. It's pretty unpleasant when a negative comes first. So let's just switch this around. Let's say this is b squared minus 4ac. B squared minus 4ac on the top of this, and then 4a squared. But this is interesting because this is a square root, and this denominator is something squared. And I know I can take the square root of the numerator and the denominator. I'm going to leave the square root of the numerator because that's definitely not something squared, but 4a squared is 2a squared. So this is square root of b squared minus 4ac all over, not under a square root, 2a, because 4a squared is 2a squared. So if I square rooted 4a squared, I would get 2a. All of this equals x plus b over 2a. Holy cow, we're so close. We're going to subtract this part on both sides, and then we'll have x by itself. What? Also, what did I forget again? I square rooted both sides and forgot my plus minus. That's a key component to this situation. Plus minus, plus minus, plus minus, plus minus. Alright, now we're going to subtract b over 2a on both sides minus b over 2a on both sides. Coming into the home stretch, scholars. Brilliant people doing this algebraic proof of the quadratic formula. Awesome. So we get x equals, now I'm rewriting it that this is coming first. I like when my x is on the left side of the equal sign. X equals negative b over 2a, negative b over 2a, plus or minus the square root of b squared minus 4ac divided by 2a. And then I see that both of these have the same denominator, so I might as well just put them together as one fraction. So we get x equals negative b plus or minus the square root of b squared minus 4ac all over 2a. Whoa! We've been using this thing for a minute, and now we know where it came from. It came from the equation, the standard form of the equation for a quadratic function. X equals negative b plus or minus the square root of b squared minus 4ac all over 2a. Alright, cool. What are we using this for? We are using this to find these roots, intercepts, solution, zeros in this crazy world that's driven by gravity. We did all this work to prove this formula, and now I'm going to show you how you can use the internet to solve these equations for you for the rest of your internet life. Okay, so you're going to get something like this on Delta Math. 4x squared plus 20x equals 20n. 4x squared plus 20x equals negative 21. Then you're going to go to Google and you're going to say, I don't really feel like solving this ever, so let's go to a quadratic formula calculator. Oh, look, quadratic formula calculator. Let's go there. And then we wait for our page to load. So it's really just like a time trade-off. You could solve it by hand or you could solve it on the internet. It's time. What do you want to do with your time? Since we have the internet available as an option, I'm just showing you that this is an option because I know you guys know how to do this by hand. You can plug in numbers, you can plug them into the calculator. It's not that interesting. 4x squared plus 20x equals negative 21. 4x squared plus 20x equals negative 21. Oh, see, now they're too tall. Plus 20x equals negative 21. Let me just double check that that was correct. 20x, negative 21. All right, and then I'm going to press solve. BT dubs, Symbolab, Symbolab is the best. Let me move that over. Symbolab has the best calculators. Okay, cool beans. Lots of answers, work going on. They're using the quadratic formula. Cool, and the second says it's reasonable. Got it. Okay, so here's our answers, negative 1.5 and negative 3.5. But this says plus or minus. What? Okay, we can just put in both answers. What was it? Negative 1.5 and negative 3.5. Negative 1.5 and negative 3.5. Let's check it out. What do you think? Are you sure you want to submit this answer? I'm pretty sure. Yay! Next, you're going to get some question like this. It's like, find the roots and the vertex of a quadratic on a calculator. Round all values to 3 decimal places if necessary. I'm going to say to you, friend, go to Desmos. Ask Desmos to do some work here. Plug in our function and we graph it, and we kind of move the graph around so that we can see these solutions. I just click on it and it's, 1.218 and 14.782. Those are the roots, and there's the vertex. Not even a problem, man. Whoa, man. Humanoid. And plug some answers in, get some questions correct. 1.218, 14.782, 8, negative 46. 8, negative 46. Moment of truth. Somebody's life's about to change. Did we plug it in right? Did we plug it in correct? I think we did. I feel good about it. You feel good about it? Are you sure? Well, what they tell us to round to? Maybe not. Round all values to 3 decimal places. I'm assuming they rounded it correctly for me. How'd you do, Desmos? Looks like you were amazing. We might also want to say, what's the axis of symmetry? Into which case we would say, I'm sorry, what? Axis of symmetry means where the parabola is symmetric, which we say what? Well, that's the part where it goes through the vertex. So the axis of symmetry is just a vertical line which has an equation x equals something, and that x equals the x coordinate of the vertex, so x equals negative b over 2a. And then we go back over here and we're like, okay, well, a equals negative 3 and b equals negative 18. So we're like, cool, we're just looking for x equals negative b over 2a, not even a problem. I'm looking for, then in this case, x equals negative, b is already negative, so negative 18 divided by 2 times a. Well, 2 times a is negative 3. Solvey, mathy. What am I going to get? Negative, positive. So positive 18 divided by negative 6. X equals negative 3. Negative 18 divided by, 18 divided by negative 6 is negative 3. Let's submit our answer. Are you sure? Yeah, dude, I'm sure. Totally sure. And that's why, because we're a bunch of geniuses. Alright, scholars, this concludes our epic discussion of the quadratic formula. You should be very proud of yourself for going through this algebraic proof of the quadratic formula. Remember to use your resources. The internet is a beautiful, wonderful thing. As always, keep on that hustle. I love you, and I'll see you next time.